Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on numerical evaluation of Bessel functions. And so far, we have discussed the fact that power series are the way to go because they are the fastest. And we discussed the power series for small arguments for Bessel function of the first kind, J nu. And we said that we do this clever factorization. And it's very easy to implement it in a sequence way. We're starting from last term and multiply them, and the lead term needs to only be calculated once. And the costly operation here is this gamma function. We looked at gamma functions as well in the previous lectures, and gamma function is also evaluated based on a power series or a series or a kind of product representation of some numbers. And we said that if we are just varying x, the clever trick here is that check for nu, because if nu is not changing, then we don't need to evaluate the gamma function each time x is changing. That's why we added a condition here to check for nu. And the reason that we could do that was because we were using the state of the object, which is a Bessel function object, to save information about the state of the object. What was the last nu that was used in the Bessel function? All right. Now I mentioned that this series, power series, works for small arguments, right? X less than 30, and numerically we saw that after x is larger than 30, the series starts to become very noisy and diverges, so it doesn't give us a stable result. Luckily, there is another way to evaluate the Bessel functions for large arguments, and that's what I'm going to discuss today. So the goal is to evaluate the Bessel function of the first kind and the second kind, y nu, the Newman function, both of them, using power series for large arguments. And it turned out when we say large argument, it's actually a very good approximation for x greater than 2. So this is actually a very good approximation based on the polynomials and power series. All right. Now the original paper came out in 1957, which is called Bessel Functions for Large Arguments by M. Goldstein. So I encourage you all to search this on Google and find it and read it. It has a very nice math about the derivation of the results. Here I'm just presenting the summary of the results or the final results. Now the one thing we notice is that if we go back and look at the Bessel functions, let's say the Bessel function of the first kind, we see that for large x there's some sort of oscillation behavior, so it's more like sine and cosine functions. But it's not perfectly sine and cosine oscillations because the amplitude, it appears to be reducing very slowly and monotonically, right? So there are some oscillations, but there is an amplitude that is reducing. The amplitude is not constant, the amplitude of the oscillations. That's where the whole idea of this representation comes from. So the idea here is that for large x, it appears that the behavior of the J nu, the Bessel function of the first kind, is some sort of amplitude as a function of x, cosine of some phase. So we have some sort of cosine behavior. The phase is changing with the x, but there is also an amplitude that is changing with x. And when we look at the plots, we see that this amplitude varies very slowly with x, right? And remember, x is getting larger and larger. And it turns out y nu actually becomes a sine function, behaves like a sine function with the same amplitude and phase for both of them. All right. So the rapid oscillations that we see in the plots of the J function here, these rapid oscillations are basically due to the cosine of the phase, and the phase term is changing with x, right? Because remember, if a and phi are big numbers, like let's say each time this phi goes through a change of 2 pi, the cosine goes through a whole cycle, right? So even if the 2 pi is maybe less than 1% of the overall magnitude of phi, it causes a big change in the cosine function, right? So the variations in phase can have a much rapid effect on the J nu than the variation on the amplitude. So the amplitude varies very slowly, and the oscillations are caused by the phase, right? And the whole idea here is to figure out approximations for the amplitude and the phase. And the nice thing about this approach, which is a very standard approach in any sort of problem that deals with waves. Why do I say waves? Because if you are familiar with wave equation, you know that Bessel functions are actually the solutions of the wave equation in a very specific coordinate system, which is the cylindrical coordinate system. So these Bessel functions are kind of related to waves, and waves oscillate with some amplitude and phase, right? That's why this whole oscillation observation comes into effect. And more generally, or in most cases, when we try to solve the wave equation, we always use this approximation of a slowly varying amplitude. So that's a very generic trick that we use when dealing with wave equation. So what is being done in this paper is that it uses a change of variable. So t is equal 1 over x, and when x goes to infinity, t goes to 0. Now, if we find an expression as a function of t, because t goes to 0, we can calculate a Taylor expansion at 0, right? For that function of t. So as x grows, t goes to 0. So first we do this change of variable, and then we do this amplitude and phase representation when x is large or t is very small. And it is always possible to write J nu and Y nu in this format, and that's because they're just part of the wave equation. So they show this oscillatory behavior for large x, right? And then it turns out for when t goes to 0, we can express J nu of x and Y nu of x in this fashion. So there is some function b nu, which is related to a nu. B nu of t over t is square root of 2t over pi times cosine of phi nu as a function of t. Remember, t is just 1 over x. Y nu of x is b nu of t over t is square root of 2t over pi sine of phi nu. So you see there are two things here. One is this amplitude is being divided by t, and in the next slide I'll show you that we actually find a polynomial or power series for this term b nu over t. But there's also a square root of t. So right off the gate, if t is negative, we see that this square root becomes a complex number, right? So that's one thing to keep in mind. And then we're going to find Taylor series for b nu over t and phi nu, right? So this square root of 2t over pi is just there. It's an analytic part of the expression, and we don't do anything with it, right? And remember, t is going to 0 because x is going to infinity. All right, here are the results. So again, these approximations are very good. When we say x is large, actually we mean x is greater than 2, which means t, which is 1 over x, is less than 0.5. So these are very good approximations. And with the t over 1 over x, the J nu and Y nu are real part and imaginary part of these terms. So this is a complex number, and J nu is the real part of this, and Y nu is the imaginary part of this. All right? Now, let's see what happens. And again, basically, we said that we have this square root of 2t over pi there, and then we're writing a polynomial for the b nu over t, which is this pa, right? And then the amplitude a nu of x, remember x is 1 over t, is the square root of 2t over pi times this polynomial pa. And then we're also writing a polynomial for phase. So phase of nu is p phi of t, which is a polynomial, over t, minus this extra phase term, nu plus 1/2 pi over 2. All right? So nu could be a real number or an integer number, right? And when it's an integer number, we see something interesting happens, right? So this whole complex term that we are calculating, the real part and imaginary part, is just our amplitude a nu times exponential of j phi nu, right? This is the standard representation of the complex number, right? amplitude and phase, e to the j times phase, and j is just square root of -1 in case you don't know. And so as you can see here, if we calculate this a nu and phi nu, which we calculate them based on calculating these polynomials pa and p phi, you see that we can immediately calculate both j nu and y nu, right? We don't need to go look for another expression for y nu. This complex number, its real part is j nu, its imaginary part is y nu, all right? Now, you see the amplitude is just square root of 2t over pi pa, and then the phase term is p phi over t, right? E to the minus j nu pi over 2, e to the minus j pi over 4, right? Now, if nu is an integer number, n pi over 2, e to the minus j pi over 2 is just minus j, right? So it becomes minus j to the power of n. And basically, and then if n is even number, minus j to the power of n becomes plus minus 1. If n is an odd number, we always end up with a j, right? So for even and odd integer indices of nu, this real part is either a cosine function or a sine function. It changes between them because this exponential term can be j or plus minus 1, right? Plus minus j or plus minus 1, right? So in general, the expansion of the phase for large x or very small t has this factor nu plus 1/2 pi over 2. And now all I have to give you is these polynomials, pa and p phi, all right? So what are these polynomials? Amplitude is square root of 2t over pi pa, the polynomial for amplitude, and the phase for parameter nu is p phi, the polynomial for the phase, divided by t minus nu plus 1/2 pi over 2. So polynomials are in terms of t, and t is 1 over x. Maybe let me write it one more time, 1 over x, all right? And pa, and luckily all these polynomials, so we're keeping a very high order, so very high accuracy, which is the 10th order. But all the odd terms are 0. We only end up with even coefficients, a2, a4, t4, a6, t6, a8, t8, a10, t10. And p phi is also the same, b2, t squared, b4, t4, b6, t6, b8, t8, b10, t10. So each polynomial has only 5 coefficients to be evaluated. And again, these coefficients have closed form expressions, so we do know what they are. So if we define this parameter p, little p, small p, as nu squared minus 1 over 4, then all of these a and b coefficients are polynomials in terms of p. So a2 is 1 over 4 times p, a4 is 5 over 32 p squared minus 3 over 8 p, a6 is 15 over 128 p3 minus 37 over 32 p squared plus 15 over 8 p, and etc. So a8, a10, b2, b4, b6, b8, b10, all right? So when x is given, we calculate t, which is 1 over x, and then we calculate these coefficients, a2, a4, a6, a8, a10, and b, and then calculate pa of t and p phi of t, and then we put them in the amplitude and phase, and then take the real part for j, and then take the imaginary part for y, all right? Now again, there are two things. Let's say we are evaluating for real numbers, t is real, but t could be positive or negative. For positive numbers, everything is okay, this square root works fine. For negative numbers, this square root becomes a purely imaginary number. So if I have a square root of minus 2, it becomes j times square root of 2, and j is just a pi over 2 phase shift. So we add a pi over 2 phase shift to the phase, right, for negative numbers. Okay, so let's head to Eclipse and try to look at the implementation. And again, this is the most efficient way of calculating the Bessel function for any large arguments, all right? So let's head to Eclipse. This is our Bessel function class. So far we have implemented jnew for small arguments, right? And we said that if new has not changed from the last new, we're not calculating the last gamma. We just use the previously calculated last gamma, right? And last gamma is a state variable. But then if new has changed, its difference from last new is greater than 0.01, which is a good measure of change. Then we update the last new, we update the last gamma, and then we calculate the lead term, x over 2 to the power of new over last gamma. And again, this works for only positive x. For negative x, the result is a complex number, which is fine, we can calculate it. All right, now jnew for large arguments. Again, the implementation is exactly what we expect. So I have t, I start with t equals 1 over x, and note that here I'm assuming x is a real number for now. And then we get to how to implement the complex one. So x is a real number, and t is 1 over x. We start with that, and then our p parameter is new squared minus 1 over 4, which is 0.25. And then we calculate a2, a4, a6, a8, and a10. What I like you to notice is that these coefficients don't depend on x. So we can implement the same logic as here. So if new has not changed, we don't need to evaluate these over and over again. So basically we can define these as state variables. So I can come here and say that double a2, a4, a6, a8, a10, and double b2, b4, b6, b8, and b10. All right, so we can define them as state variables, and then the default is that the index is 0, so we can calculate them for 0, or we can just and then here we checked whether or not the new has changed. If new has changed, then so maybe let me copy these from all right, so I'm going to copy them in the constructor, for example, and then in the constructor a2, a4, a6, a8, and a10. all right, so these are, and then p. What is p here? P is let's define this as last new times last new minus 0.25. all right, and we can even define a parameter last p, for example. So last new, last gamma, double it's not necessary. So this is our a, right? And then here we use the same thing here. So if new minus last new is less than basically 0.01, we don't need to do anything. Otherwise we update the coefficients. So I'm going to comment these, and then update last new and update a2, a4, a6, a8, and a10. all right, so a2, a4, a6, a8, a10, and then based on these we just calculate we actually didn't need this condition, but let's keep it for now. Similarly, the same thing for b. So we can copy all these terms and calculate them in the constructor. b2, b4, b6, b8, and b10. all right, And then I can again copy it from here. Let's also comment it and calculate them in the else statement here. So only if new has changed, we're going to update these b parameters. Otherwise, if only x is changing, we don't need to go through all these multiplications each time, which, I mean, it doesn't add much computation cost because these are just numbers, polynomials. So this is not some sort of elementary function like sine, cosine that takes some work for CPU. But we are saying that we want the utmost efficient implementation, all right? So polyamp, polyphi, this is PA, this is P phi, 1 plus B2 T squared, B4, T4, B6, T6, etc. So if T is real and positive, we just calculate the square root of 2T over pi, this polyamp times cosine, because remember we're calculating the real part. Cosine of the polyphase over T minus nu plus half pi over 2, all right? But if T is negative, we calculate minus T, all right, in the square root, so minus T is positive. But then a square root of minus 1 gives us J. J is e to the J pi over 2, so it's a pi over 2 phase shift. So we can add this pi over 2 here to the phase, right? Cosine poly phi over T minus nu plus half pi over 2 plus half pi, all right? And we already know that cosine of something plus pi over 2 is minus sine of something. So we can also implement it based on sine. So, but for symmetry, let's just keep it as an extra phase, all right? So let's go to, let's create a test class here. Class test Bessel large. All right, so here I'm going to create test1, and let's implement test1, public static void test1. All right, now in the test1 I'm going to create obviously a Bessel function object. Bessel equals a new Bessel function. All right, and then I'm going to create an array of x values, double x mathUtil dot linear space from we said that the approximation for large x is valid for x greater than 2. Let's go from 5, for example, to 100 with 1000 terms. All right, and then double J0, for example, array func dot apply t goes to Bessel dot j new large. We're just looking at the large argument with real numbers, so 0 and t, and then we apply the x array to it. All right, and similarly j1, j2, j3, j4, j0, j1, j2, and j3, 1, 2, 3, and then we plot them. So MATLAB chart, fig new MATLAB chart, and then fig dot plot x and j0 with color B, j1, j2, j3, fig dot render plot, fig dot show with an exit flag. So j1, j2, j3, blue, red, black, and green. All right, so let's run it. It doesn't show the plot because I'm on a Mac, so I have to go to run configuration. In the arguments, I have to remove this VM argument. Now it shows, and as you can see, we see the oscillations, and it looks okay. For J0, J1, J2, J3, let's also time it. So timer, new timer from mathlib, and timer dot start, and then after the calculations, timer dot stop, timer dot show. Takes about 6 milliseconds. Just I want to give you a second, just wonder it. 6 milliseconds to calculate 4,000 times the Bessel function. This is impressively fast. It's even faster than the previous case for a small argument, because in the small argument we had that gamma function, which takes a little bit of time. But here we absolutely have nothing. The only thing we have is two polynomials, which have absolutely no time to calculate, and then a square root, which is pretty fast, and then a sine and cosine function. Sine function for the j nu, and cosine function for j nu, because we're calculating the real part, and basically sine function for y nu, because we're calculating the imaginary part. All right, so impressively fast. And we can also test this, and again against Python, for example. So I can export this. You already know the routine. Export this as a text file, and then import it into Python. So now it's on my desktop. I can open it in a text file, and then copy everything, and then go to my browser, which already has a Jupyter notebook. Let's paste all the data files. So we have J0, J1, J2, J3, so 4 figures, and we want to plot plt plot x0, y0, color B, and then label Java. All right, so we want to plot this, and then we want to also plot this using the x values, but evaluate the j nu 0 and x nu red. We give it the label of Python, and we have the line style of dash, style dash, and then we want to turn the legend on, plt legend. All right, so as you can see, we have a perfect fit, and we are going from 5 to like 100. So that approximation, that when we say for large arguments, it turned out this very fast approximation has an extremely good accuracy up to x equals 2, so 2.53. So we can actually see how good the approximation is. So let's reduce this from 1 to 100 and plot it. Now you see, I mean, it gets very bad, right? So 1 is not good. Let's say 2.5. 6 milliseconds. We still see the oscillation, so looks pretty good. Let's export it to a text file. All right. And let's open it in a text editor, and then copy all the stuff. And then let's go back to our browser and paste the new values here. And now you can see, even from 2.5, we get a very good match to Python, right? And remember, all these numbers, evaluations, which is about 4,000 times, took only 6 milliseconds. So this equation for Bessel function is extremely fast, which is very good, right? All right, so this was the implementation of the Bessel function, right? And we said that if nu is not changing, we're not calculating these coefficients over and over again, right? We only look at the we only update these coefficients when nu is actually changing, because most of the time the nu is fixed and x is changing. So we save some numerical computation. Okay, now as you can guess, we can have also y nu of large arguments, and here instead of having the let me remove this, and again we can have the same thing. So let me basically everything here is the same. The only thing at the end is these. So we haven't discussed y nu yet, but when we get to that, we're going to discuss the large argument evaluation, right? So now we have a j nu a small argument for Bessel function for any double value and x, a real number, and we have a large. So what we're going to do, we're going to write a method j nu that evaluates Bessel function of the first kind for any real nu and any real x, right? So the first condition, obviously we have to have 2 or 3 conditions. 2 conditions for checking whether or not we're dealing with small arguments or large arguments, right? So the first condition is that if nu is not an integer and x is negative, okay, then our small argument approximation has a problem in this power, right? And the result is basically becomes a complex number. So we have to check for that, and the reason is that this method is supposed to return a double. That's why I'm looking at it and say, okay, if nu is not integer and x is x is negative. Now remember, the small argument approximation works between 0 and 30 for positive or negative. I'm saying that, okay, I couldn't calculate the j nu, and you need to pass x as a complex number. And when the user passes it as a complex number, and by a complex number is, we're saying that just pass x as x plus j times 0 times j. So it doesn't have an imaginary part, but it's a complex object. And once that happens, then the compiler, instead of choosing this method, goes and chooses this method that has a complex argument, and then this power is calculated based on the complex power, not the real power, and then it has no problem raising a negative number to some real power. Okay, so the complex value of the Bessel function gets evaluated. But for the large argument, we didn't have this problem. It worked for integer and non-integer, whether or not the x is basically whether or not the x is positive or negative didn't matter in terms of relation to nu. Nu could be any number in this equation. If x is negative, we already took care of it by defining a pi over 2 phase shift to our cosine function. So everything works fine. There is nothing to worry about there. All right. So this is the first check for our small argument expansion. And then the next thing is to check whether or not nu is an integer. I mean, it's not necessary, but we can check it. And if it's an integer, then the question here is that if it's less than 30, we again, if nu is positive, yeah, what we can do, this is not necessary, but we're saying that if nu is integer, then j minus nu becomes minus 1 to the power of nu, which is plus or minus. So I'm checking if minus nu, which is a positive integer, whether or not it's an even or odd number. And then I go and calculate the positive index of the Bessel function. It's not necessary, but we can do it. It's a valid argument. The same thing for the large argument, right? If nu is integer, then j minus nu is minus 1 to the power of nu j nu, and minus 1 to an integer power is plus or minus 1, depending on whether nu is positive or negative, depending on whether nu is an even integer or an odd integer. All right. Okay, so I mean, for jn, we can just invoke j nu and pass our argument, right? And we have already discussed the complex implementation of j nu, and similar thing we can do the large, basically the large argument for complex relations, and we're going to look at it in the next lecture. What I would like to point out here is that I defined the j nu and y nu based on the real and imaginary parts of a complex number here, and the real part is always real, and imaginary part is also always a real number. So This definition works for real x values. When x becomes complex, we have to modify this definition a little bit, and we'll look at how we can actually do it in the next lecture. Thank you for watching, and I'll see you in the next one.